nitric acid and sulfuric acid mixed together. And then by looking at the reagent, you can figure out what reaction it is. Nitric acid, sulfuric acid mixed together, that will produce nitronium ion. The nitronium ion is electrophile, and that's the one that gets attacked by the benzene. The benzene, high electron, is going to attack the nitronium ion there. And but we have choices where the nitro group is going to go. Let's say we have this nitro group, the para position drawn like this. Then because of double bond drawn this way, it's going to be making the carbocation on the meta positions, right? And then if you have a hydrogen taken away, then that will make this paranitro compounds right there. It also can make it happen on the older positions, then it's really make that sigma complexes, and then proton goes away, you get the older substitutions. These two will be the major products. You may expect that maybe it can go to meta position, but it won't happen. The reason why you won't get a meta position is because you don't get this extra stabilizing sigma complex by the alkyl substituents. And then of course, you don't see this one here, but this carbocation can move to there by the resonance structures, and that's the reason why ortho gets substituted, para gets substituted by the meta positions. Now the reaction here is a substituted benzene. Benzene has a substitution here. And then we have a reagent, bromine with a ferric bromide. If you mix the bromine with the ferric bromide, what happens is you're creating like an electrophilic bromine. You may call it brominium ion in extreme cases. It will never be like this, but for the solving the problem, I guess you can probably consider that. This combination will make a brominium ion, and that's going to be get into the benzene ring. The question is, where it's going to go? To determine that, we need to think about what type of substituents is this. This is an ester carbonyl directly on benzene. Is this electron donating groups? And you should say no, right? Because the carbonyl is electron deficient species. So that's electron withdrawing groups. Electron withdrawing groups doesn't want to make the electrophile go to the ortho or para position, because that makes it terrible. So what's possible? It actually better wants to make the something of this brominium ion go to meta position. So it makes initially forms a carbocation in the para position that can move around the ring by the resonance structure, but it will never be at the carbon bearing the ester carbonyl. It always avoid that position, regardless what resonance structure you draw. So that's the basic reason why that's better than the other positions. Eventually, the proton goes away, and then you get bromine substituted the meta positions. So after the carbonyl is a meta directors, so that's why it goes to the meta position. You can remember that way. But as I said, the reason why it goes meta position is always the para position makes it really, really bad. They want to avoid that. And the meta is just, it's not as worse as that. The reactions are slow because they're withdrawing groups of the benzene, that kind of slow the reaction down because of high electron density of the electron withdrawing group substituting benzenes are lower. So it doesn't make a nucleophilic attack as well as the one that had the donating groups. So anyway, so this is the kind of things that we need to consider for solving problems like this. This question is what I really like. And this question is something that you want to pay attention closely because we always ask this type of question in the test. Believe me, a lot of people fail to understand this. So let's talk about the reaction here. It is a nitric acid, sulfuric acid mixed together, right? So reagents are kind of telling us what reaction it is. Mixing nitric acid, sulfuric acid together, it creates nitronium ion, right? Nitronium ion is the electrophile. Where that is going to go to the benzene ring, that's the question. And then this benzene has a amine already substituted. So if you remember those charts we talked about, there are variety of the substituents. You have the donating groups, you have the joining groups. If you look at the amino groups, that is electron donating, right? And that is actually something we consider really powerful electron donating groups, high donor, because of the nitrogen has a low pair. So what this high donor does for the substitution is, it makes the reaction go faster, first of all, that's why we call it activators. And it is also paradirectors. So because of that, nitro group, nitrogen ions, will be probably added either also position or the para position, not the meta position, because of amino groups is a strong activators, high donor, and it's also paradirector. That's what chart shows you, right? So, and then you have a nitro groups, like and in the para position, you get these sigma complexes, but when you draw the resonance structures, it goes to the carbon where the nitro group, amino groups here. You can see that these two will make the extra resonance structures, and that's the reason why the ortho pairs are better substitutions. And eventually, this proton goes away, then you get the aromatic benzene back, but that have a nitro go substitute in the para position. I mean, I only draw the para substitutions, but you can also see that the ortho position can be also substituted by the same reason. That's what we call ortho paradirector, not just ortho director or the paradirectors, right? So either is fine, but at least you can say that why the nitro goes the para position to the amino groups, because amine is electron donating groups. That makes them use this low pair to extra stabilizing sigma complexes. So you would most likely answer this as an answer, and I'm pretty sure that you'll be proud because you can get through the whole thing and finally get the products. And then, as I said, ortho can be also produced too. I mean, you don't need to show me both. You can show me either. I'm going to assume that you meant both, whether it be for one. But still, for this question, I'm going to say you are wrong. So why do you think I put that answers, which I solved it out, and I gave the reasons, and then I still cross the answers out? Why that is wrong? So this is the part that a lot of people miss, and then they get it wrong when they see this question in the test. So I'm going to explain why. This is kind of tricky. Electron withdrawing, I mean, the amino group's electron donating group, that fact doesn't change. It's a strong electron donating groups. Electron bound is going to be added either ortho or para position because of it makes it more stabilized intermediate. That fact doesn't change. That is absolutely fine. That part is not wrong. What is the problem is the condition of the reaction has a very strong acid. Nitric acid, sulfuric acid mixed together. You can see that these two strong acids mixed together is a very, very acidic solutions. And then this acidic solution, what they do to the amine, when amine reaches the base, when base sees acid, then what happens? They neutralize. That's the first reaction happened. So what happened was this strong acid will protonate the amine. It's unavoidable because that's a base, and this is strong acid. So by mixing these together, of course, you mix these together, make a nitrogen ion, but these reactor molecules still in the same solutions. So the acid will protonate an amine that change to the ammonium groups. And then ammonium group is a positively charged. So is this filled electron donating groups? This one is a positively charged, it's electron deficient. So by being protonated, amine change the ammonium groups, change to very strong electron withdrawing groups from the strong electron donating. it changes itself because of the reaction is carried out in acidic condition. So it becomes an ammonium groups, and then it changes everything. Now, because that's electron withdrawing groups, it doesn't want to make things happen at orbital para positions. Meta position is willing to make it happen because that is not as bad as orbital para positions. So when it becomes a protonated, it becomes an ammonium groups, nitration will happen at the meta position, not the orbital para position. Of course, it will make a sigma complex that's withdrawn. Eventually, the proton goes away, make the benzene. You get the ammonium groups here with the nitro at the meta position. But the ammonium group can lose a proton to the solvent at the end of the reactions. You get amino at there and then nitro in the meta position. That is the answer. So I want you to see the differences. Why amine, which is a strong activator, high donor, and also parareactors, make the nitration reaction go to the meta position. It's all because amine will be protonated. And then once it becomes a protonated, it becomes a very strong electron withdrawing group, and that becomes a meta reactor. But at the end of the reaction, proton goes away to the solvent, it becomes an amine again. That's why it looks like the amine became a meta directors, but it was because the amine was ammonium groups when the reaction happened. So this is kind of a tricky question. I really want you to think about this carefully, because we ask these questions a lot in the text. Any question on this? All right, next one. Now you're probably going to see some questions showing that, how are you going to make these products? I mean, this is given as a product, you want to make it. Then you need to think about, where you're going to start. Essentially, we got the molecule has a hydroxyl groups and the chlorine groups. So we can start either. We can start from the one with the chlorine, we can start one with the hydroxyl groups, then second substitution can be added by the reactions. Right now, we don't know how to add the hydroxyl groups. If you remember that, electrophilic aromatic substitution reactions are very limited. Only 5 different things we can do. Of course, 3 things we did: halogenation, nitration, sulfonation, and then adding 2 carbon chain that we will discuss later. Just the 5. We don't have any tool to add the hydroxyl groups yet. So, it will be possible later. So that's a nucleophilic aromatic substitution reaction we'll talk about. But right now, we don't know how to do this part. So that's why this is not something we should consider. We should think about, if you started from the hydroxyl groups in the ring already, then will you be able to make the chlorine go to that position? Okay. And then the hydroxyl groups, the phenol, the hydroxyl group is an electron donating group, it's a pi donor, it's an orbital parallel vectors. So if you do the reaction, like chlorination reaction, chlorine gas with the aluminum chloride, then it can go either para position or the orbital positions. So we think these can be produced from that. And you can see here that it makes the sigma complexes, having this carbocation next to the hydroxyl groups makes it extra stabilizing sigma the resonance structure there. That's the reason why it becomes orbital parallel vectors. But eventually, lose the hydrogen, then you get this made. This is not the only one you makes it. You also makes it with the older substituted one, but because that gets produced, we may assume that we can separate those two, and that's the reason why we can make that.